Imagine we had a titration whereby we have two chemicals. One is our unknown. Okay, is going to be here in the burette. And this is going to be sulfuric acid, so H2SO4. On the other hand, you have a known solution of a specific concentration and volume, and this is, in this case, going to be sodium hydroxide. Okay, we know the volume because we have used a pipette, and therefore we have 25 centimeter cubed, or 25 mil. And we know the concentration because our stock solution that we've taken it from, okay, reads a concentration of 0.105 mole per decimeter cubed. So you've run the titration, first of all doing a trial titration, working out roughly that it was occurring at 20.50 centimeter cubed. This, okay, remember, always in all of these values to be recording them to 2 decimal places, with the second decimal place, okay, either being a 0 or a 5. So either second decimal place, either 0 or 5. How to read to these 2 decimal places? Well, here is an example of a burette. This is on meniscus at this point here. So we are looking at the bottom of the meniscus, kind of just here. So, first of all, we know it's between 19 and 20. Okay, it's not 20, so it must be 19 point something. If you count here, 1, 2, 3, 4. So it's 4. It's not got quite to 5. However, I wouldn't say that was 4.0. I would actually say it's 19.45 because it's just past the 4 and close to the 5. So with our title of results, we are looking, okay, at the values here, the differences, and whether or not they are, first of all, what we call concordant titers. These are titers that are within 0.10 centimeter cubed of one another. So, given the example shown in this table, we can see that both 19.10 and 19.05 are within this range. However, the 18.90 is not within this range. This then allows us, okay, after doing this, to look at step 1 of our calculations. So, having identified the concordant titers, we need to calculate the mean of the titers. So in this case, we are only going to use 19.05 and 19.10. And it's quite simple, because we have 2 values, we just need to add those together and divide by 2. This gives us 19.075 centimeter cubed. Okay, but what's important at this stage, although we've got these values, later on we are going to be working in decimeter cubed. So we need to convert this to decimeter cubed. To do this, we know that there are 1000 centimeter cubed in 1 decimeter. Okay, so the calculation is quite simple. We just take 19.075 centimeter cubed, okay, and just divide by 1000. This gives us 0.019075 decimeter cubed, and we will be using this value later on. Step 2, after working out the mean of the titer values that you have been looking at, is to construct a balanced equation for the reaction that is actually occurring between the reagent in the burette and the reagent in the conical flask. So if we think back, what we had, okay, is in the burette we had H2SO4, sulfuric acid, and then in our conical flask we have sodium hydroxide. So we construct a balanced equation using the stoichiometry, so we know that that is obviously going to form sodium sulfate, salt, and water. Obviously we're not happy that we've got 2 sodiums on this side and only 1 sodium on this side, so to balance this out we need to put 2 NaOH, but then obviously this leaves 2 OH on this side, okay, and only 1 OH accounted for on this side, so we put 2 there. The important relationship here is that for every 1 mole of sulfuric acid, we are going to be reacting it with 2 moles of sodium hydroxide in order to cause neutralization, because as this is basically what is happening at the end point to show the colour change. Step 3 involves calculating the number of moles of your known reagent, which we're just going to call N brackets known. Okay, so if you remember from the beginning, we had a conical flask of which we've used a pipette to put in 25 ml of sodium hydroxide. Now, it's from a stock solution which had a concentration given of 0.105 moles per decimeter cubed. So, to work out the number of moles of sodium hydroxide, what we need to do is use this information here. Now, first of all, we need to convert milliliters or centimeter cubed, depending on what is given, to decimeters. So just like before, we need to take 25 mil centimeter cubed into decimeter cubed. Okay, so that just means, again, just dividing by 1,000, so we can work out our volume equals 0.025 decimeter cubed. So we've got the volume now and we've got the concentration. So it's a case of just using our number of moles equals volume times concentration equation to work out the number of moles for this. So inputting the numbers, okay, and make sure whenever you're doing these calculations to always keep the units. So the concentration there is 0.014 mole per decimeter cubed. That way, if you make a mistake, at least the examiner can see. If you do that calculation, you work out that there's 2.625 times 10 to the minus 3 moles. Step 4 involves using the mole relation that we worked out in step 2 to work out number of moles of the unknown. So the balanced equation shows that 2 moles of sodium hydroxide gives 1 mole of sulfuric acid, H2SO4. So this basically means that we have N of known that we've already calculated divided by 2 will give us N of unknown. If we plug in the numbers that we've already given, we've worked out that number of known, okay, so number of moles of NaOH equals 2.625 times 10 to the minus 3 moles. Therefore, number of moles of the unknown, okay, which is H2SO4, will be 2.625 times 10 to the minus 3 moles divided by 2, which equals 1.3125 times 10 to the minus 3 moles. And that is basically just plugging the numbers into this equation here. The last step, step 5, is to using what we've just worked out, number of moles of unknown, by using the balanced equation mole relationship, with the information of the mean titra that we've done using our barrette, okay, in decimeter cube, to calculate C, concentration of the unknown. So that's basically using this equation here. Number of moles equals volume times concentration. Thus, to work out concentration, we just need to do a rearrangement, basically making C the term, so bring that over. We have concentration equals number of moles divided by volume. As I said, we just worked out number of moles, so we're referring to of H2SO4, which is our unknown, okay, concentration that we're looking for. We've just calculated that we have 1.3125 times 10 to minus 3 moles that we've been reacting with, and our mean titer value, which we've worked out in step 1 in decimeter cubed, was 0.019075 dm cubed. If you just do the division there, that gives you the answer of 0.06881 mole dm minus 3, which is the concentration units. So that is the answer for working out the concentration of H2SO4, our unknown. Now it is important because now this was the initial piece of information of our known standard solution, the volume and the concentration that we were given. So we have to use we are limited by the significant figures of the information that we are given. In this case, we are given 3 significant figures, okay, being our limit in mole dm cubed. So, as this stands, our actual answer is incorrect, okay, so we need to just round that up to 3 significant figures, okay. Obviously, any zeros are not significant, so 688 mole dm cubed is the correct answer, okay, based on using our limitations of accuracy with only these 3 significant figures here. So all this leaves me to talk through some top tips when doing concentration calculations, which are particularly important in the exam. Okay, so you always want to be writing down the units of each and every value you use. This is important, so if it's moles, put moles, if it's concentration, put moles per decimeter minus 3. And this is actually tied in with this point here of double checking that you've always converted centimeter cubed or mil, so that's particularly important when dealing with titers, okay, into decimeter cubed. Remember, we do this because concentration is expressed as moles per decimeter cubed, not moles per centimeter cubed. So that can sometimes lead a big issue. Going back here, just clearly show what you are doing, okay, so show it step by step as you go through a calculation, and show clearly the formulas that you're using, whether they've been rearranged or whatever. And then finally, just remember your answer can only be accurate to the number of significant figures given in the information you're given at the beginning. Okay, so if you're given 3 significant figures as your information at the beginning, your answer needs to be 3 significant. If you're given only 2 significant figures for the concentration at the beginning, then your answer needs to be 2 significant figures.